All right, so Matt, thanks for the opportunity to have you to let me speak today. Pleasure to do it. So we've been working with SwRI on a project called ConnTact. They're going to talk more about what John probably is going to be talking more about what he's doing with that project. So Matt asked me just to give a little kind of background and motivation behind why NIST is interested in this. ConnTact is really allowing for more flexibility and adaptability and agility in performing various types of tasks with very minimal programming that happens up front. So that's an area that's of great interest to NIST. So for those of you that aren't as familiar with NIST, we're the National Institute of Standards and Technology. We have a program that's focused on robotics, which is measurement science for manufacturing robotics. The program's been going on for quite some time, and I helped to coordinate this program. So I just have a few slides, and then I'm not going to take very much time at all, and then I'm going to turn it over to John and the SwRI folks. But just as kind of a big picture, this is the blobs there represent projects within our program. We have ones focusing on perception and grasping and mobility and AI and HRI and things of that sort. The part that is of most relevance, I think, to what you're going to be hearing and the work that we're doing with SwRI is the middle box on the right, the agility performance robotic systems. So I'm going to talk, I can talk for hours about these projects. I won't, because I'm just going to focus on what's important here. But if anybody has any questions about any of the work that we're doing, I'm happy to go into some of the other efforts. So why this is what we're interested in. So when we look at robot agility, we can kind of break that into hardware agility and software agility. So hardware agility is how can different hardware configurations affect a robot's ability to accomplish a variety of tasks. That's important, but that's not what the focus is of our interest in this project. What we're really looking at is what we're calling software agility. So how can a robot be quickly tasked to perform an operation? How well can a robot adapt and respond to task failures? How well can the robot replan when a new goal is provided for it? How to allow for interchangeability of robots and things of that sort. So those are the core questions that we're trying to really get our hands around and come up with standards and performance metrics and approaches in order to address. So why do we focus on these areas? We kept on hearing the same thing over and over again from various stakeholders. We've reviewed roadmaps, number of site visits, went to conferences, and what we hear over and over again are robots take a long time to program. They're incapable of adapting to changing environments. Often when a company decides on a robot brand, they're tied to that brand because of the huge upfront costs they have to go through of getting things set up and programming it and safety aspects and things of that sort. And then training a robot to perform a new task is very time consuming and not cost effective. And so those are the things that we're trying to get around. This is my last slide. So this is does it come through? Yeah. So this is just an eye chart. There won't be a quiz on this at the end, I promise. But what we did is we tried to go through and say, okay, what would it take to make a robot be agile? And this was our initial attempt at it. And there's so many parts that go into it, right? So the first thing, which is these purple boxes, there's one around ontology at the bottom there, and one around MySQL database is, there's a lot of knowledge that the robots need in order to allow them to be agile. If you compare that to a person, for example, the amount of knowledge that somebody needs just to perform often the simplest tasks is immense. And so we need to have that knowledge be available to the robot itself. It's got to understand its own capabilities. That's that red box at the top. So it knows how far it can reach, how heavy of something it can lift, essentially what it's capable of doing. And then it's got to be able to plan. So that's that light blue box, right? It's got to take this knowledge of itself and the environment and what it's trying to accomplish and come up with a plan, probably a high level abstract plan and a low level detailed plan in order to actually make that happen. And then the last box, which we're very interested in, is the green box there, which is metrics, right? So, okay, so now we have a system that is supposedly agile. How do we know that it's agile? How do we compare it to other systems? How do we measure it? So we have efforts going on in all of these areas, but the part that I think many of these touch what you're going to hear next from John and the SwRI guys on the ConnTact work. And it's kind of bringing together a lot of this information, the planning, the knowledge, and things of that sort in order to allow these systems to be more agile. So very happy to be working with SwRI, and that was kind of an abstract description, but I now turn it over to them to go into more details.
Thanks, Craig. Yeah, I'm John Bonnin. I've been doing most of the work on this ConnTact framework. We were tasked a year ago to try and work on this agility problem. with the goal, of course, to make it easy to set up, modify and repurpose. And we've also been aiming at hardware agnostic systems, like Craig mentioned, so that it doesn't matter what robot you have, someone else's algorithm or solution might be compatible with your system. And we've been focusing especially, just for our own development purposes, on a compliant robotics assembly cell, but you can certainly substitute in any task and any sensing methods and any solution that you want. So we chose this because it's pretty challenging and it's kind of a new avenue of using robots. We've got here a UR10E, which has this nice force and torque sensor in the end, and it's running a real-time motion controller called Cartesian compliance controllers, which is driving the robot to avoid forces that it detects. You see, I'm pulling on it and it just kind of plays along with me. This allows the robot to be in collision with objects and feel around on surfaces for features. And this actually makes assembly a lot more human-like. So if you can figure out how you yourself assemble something with your hand, for instance, putting a peg in a hole without looking, if you have a general idea of where the hole is, that is, this robot system is pretty capable of doing that. All you need to do is come up with an algorithm, but you can also use this framework we've developed for all kinds of other applications. You can use machine learned solutions. It's all about sticking together the hardware, the overall plan, and the minute motions required. So the work we've mostly done is developing this structure, this topology here. We're trying to, let me see here. The main goal is to abstract as much as possible and pull things apart into a few different levels of control. We've got an interface and environment. And then within the environment, we've got an overall, can you see my mouse pointer? I'm trying to point with it. We've got an overall state machine defining, okay, here are the major steps. And then within the state machine, we want to be able to define minor steps to do small kind of repetitive feeling or sensing or manipulating tasks. So I'll walk through these one at a time. At the top here, we've got ConnTact interface, which is shown between the rest of the system and your physical system. So whatever robots and sensors and workpieces you have is in the physical world. We've defined this interface, which is a bunch of abstract functions, which as long as you define them all and they all work, the rest of ConnTact, the framework, will function. So that allows you to write a ConnTact interface for your specific hardware and software solution. We don't even assume you're using ROS, though so far we've only made a ROS and a ROS-II ConnTact interface. As long as you get that right, the hardware agnosticism is mostly in the bag. I don't have much examples on that, and that one's still under development, but there's some good work gone into that. Beyond this, we've got an environment for abstracting away the positional specificity of your task. All right, so we've abstracted out all the hardware, and then we abstract out the position. What I mean is, if you can define the task location in robot space, context basically reorients and changes the transformations from wherever the robot physically is to task space. If you're trying to do a task like inserting a screw, we have an example task here, insert screw ConnTask. The task space would be centered on the screw hole instead of some position in robot space. And so from that point, you can define your algorithm as a state machine or whatever you need to do. And the position 0, 0, 0 is always going to be the location of whatever goal position your assembly needs to attain. So context is removing the location and orientation uncertainty. Within there, we've got this ConnTask object, which is a state machine. We're doing algorithmic assembly here, no learning, but this moves from finding the surface for certain and then carrying out each of the subsequent steps to actually perform the, in this case, insertion of a screw. And then within there, the state machine is given functionality by associating a behavior with each state. So the ConnTask here is a flowchart. It's a state machine. It's got blocks and arrows pointing between the blocks, depending on the exit states. And we realize each of those blocks, each of those states using this constep object. Yes, there's a naming scheme. And these essentially comprise a motion policy. So we move in a certain direction, or we're doing some sort of sequence of small motions, and exit conditions, which can send you to a new state. And then, since this is an assembly task, and theoretically all of the tasks you're using a similar algorithm on might have different scalars to make it work for different work pieces, we've got the idea of importing a config. And so we've got a screw insertion task. So we suppose that the user might want one set of scalars for an M6 screw, one for an M8 screw, one for a quarter 20, etc. So we've got this highly abstract environment here, which leaves out all the specifics of your robot, your control system, even your location. And then this algorithm with its different behaviors runs inside there. And so your main user program can command different tasks to execute, one for each screw, or inserting plugs, or assembling gears, or whatever your application is. So to break this down just a little bit more, I'm going to blaze through the actual setup of our example solution. Here's what we call the spiral search peg insertion demo. We accomplished this. You see the robot in the upper left. We told it the wrong location of this hole. So the robot bumps into the table and compliantly does not try to push through it. It detects the obstacle of the table, spirals outward, and then when it drops into the hole, it follows it in. And on the lower right, we've got a nice graph of the spiral forming. This is our example, like our most basic assembly task. And by developing this and then abstracting everything out, we've built out the solution over the last year of development. And I want to emphasize by showing you like the innards of this application, how little actual work went into it. This is an algorithmic solution, but imagine you've got your learned policy. It should be almost equally easy to pass in all of the needed information. Here's where we declare a state machine in the ConnTact object. Okay, the ConnTact is the state machine algorithm that gets the task done from start to finish. We declare several states here, and then we declare the transitions between them. We're just using the PyTransitions module, which makes it easy to do a simple state machine this way. These are all the transitions from one state to another. And then to realize our low-level granular motion and exit condition policies, we associate a constep object, one of these step behavior objects, with each state. And these are highly reusable. So we use one that finds a surface that's supposed to be in a general cardinal direction. And we use the same one again for inserting the peg once we've found the location of the hole. And then we just instantiate the thing and run it. So this is the ConnTact definition. We've got a little bit more stuff below it to define the plotting and to do a bunch of YAML file reading, but that's all kind of task specific. This is the meat of the state machine definition. And then to give behavior to each of those states, you inherit the constep like root object and then override a couple of items within. You can, of course, define a much more complicated motion profile. But for our assembly task, a lot of times you just need to move in a direction until you run into something. So we say we're going to comply along the z-axis, and we're going to try to hold to 0, 0 in the x and y axes. And then how do we move the robot? We just apply a 7 Newton downward force. So we define a very simple movement policy, and then we exit this state whenever the robot is static and it's in collision, which means it detects the same force coming back, which it's applying. So if it feels 7 Newtons up, it'll know it's run into something and it's stopped. And then when we exit, we just record the location of the surface height. In our application, we're not assuming we know where the exact height of the board is, and we don't want to start in collision. So we just kind of advance until we find it. That's the entire behavior defined here. And then to define the spiraling behavior, we wrote some code which defines a plane spiral. It's just a parametric math. And then we similarly override a handful of the movement variables. And then we define an exit condition that, hey, when our Z component of the robot position drops below the recorded surface height, we know we're in the hole. We can't be anywhere else. And so we advance to the next step. So we've got these highly granular blocks here, which you slot into your state machine, and you can put any motion policy in that you want. We've got our default one, which moves in a direction under a certain amount of force, but it's easy to subvert that and go with a different policy. So we've got our little summaries here. Move down until you bump into something and record the height, and move outward in a spiral until you drop past the surface. And there are a couple other steps, but they look a lot more like fine surface. And then the ROS node has, well, we've got one con task needed. We have one workpiece. We want to insert this peg. And so we give it a reference to that object, that solution, the algorithm. Then we instantiate that interface and the context environment. All right, so this one listens to our hardware under parameters. And then the context, we feed it the desired location of the hole. Those two are persistent. So we do that once at the top of the node. And then we only have one peg here, but for each peg, you would instantiate your task object and feed it its parameters config file, and then just tell it to go, and it executes. We are pretty confident that this node is pretty similar to anything that would be developed for other applications. It's representative. So to summarize, this very simple solution here only took us 230 lines of unique code and 2 YAML files just to define the scalars, which I hope comes across that it's modular and it's easy enough to swap out any of these pieces which aren't relevant to you. And we provide a lot of resources in the package, which should be useful for most applications, this finding surface behavior, this dealing with a compliant robot behavior. So as we're going forward this year, we're finishing out the ROS-I support, which is just making another one of those interface files. We hope that it's easy enough to make other interfaces if you need them. And we're working on more example applications and doing a couple of projects using this framework. So I hope that gives you a little bit of an insight into what ConnTact is all about. And I hope it demonstrates that we're aiming at that agility goal very directly. And I hope that we get some participation from the community to help us refine it and see if we need to develop further to accommodate more of the machine learned policies and solutions, and hopefully get a lot more assembly robots working in the field. That's all I got, Matt. Questions?
I have a question, John.
Yes, sir.
It looks like that assumes the surface is flat and perpendicular and non-compliant. Is that true? And if so, are there other things you're working on to make it work in different situations?
Right now, if the board was in a different orientation and location, we would feed that new location and orientation into the context, that environment, and it would be able to compensate for that. I haven't shown a video of that yet. But yeah, we are assuming that it's going to be flat and it's going to be solid. So to accommodate those, I think that's task specific enough that we could let the user tackle those problems, I think. Does that make sense?
Yep. Yeah, I just wanted a little more detail on that. Thank you. That's great.